Hi, hello, how are you? Good evening, welcome to India's number one online platform, Gradeup, and welcome to my class of operating system. So today we will see about hashed page table and inverted page table, and we will do lot of question today in the class. So please join me quickly and then we start the session. The topic of today is A to Z of hash page table and inverted page table. Why we need this table? Why we need this table? So quickly subscribe the channel, like the channel, and please share the channel with your friends, with your juniors, and click on the bell icon. Correct? So here, this is all about me. My name is Navneet Gupta and I have 8 years of teaching experience. I got 92nd rank in GATE 2008 and many more things. You can just read it out here. Correct? So here is the question number for you. Here logical address is equal to 32. RAM size is 4 MB. Frame size is 512 KB. Find the bit for page number, page offset, frame number, frame offset, LAS, page table size. Okay, so we have to find all these things. I will give you 1 minute, then I will explain the question. Okay. So in this question, what is given? Logical address. You know logical address is divided into two portions. One is P and one is D. P means page number. The value of this bit will be page number value, and the value of D in the decimal will be page offset. So here the complete logical address is given as 32 bit. Okay, now here you know 2 की power D is equal to 1 second. Give me a minute. Right? Okay, so you know 2 raised to power D is equal to page size, or page size is equal to frame size, and they have given frame size is 512 KB. So 2 की power D will be 512 KB. So you can write 2 raised to power D is equal to 500 is 2 की power 9 and K means 2 की power 10. Okay, and it is in the byte. So it will be 2 की power d is equal to 2 की power 19 byte. So finally d is equal to 19. We got it. So the value of d is 19. Right. So this is 19. So p will be 32 minus 19. यानी कि it will be 20, 12 plus 1, 13. So it is 13. So finally we got page number. Bits for page number is 13. Page offset is 19. Frame number. So I told you page size and frame size both are equal, and also they have given the physical address. Okay, so physical address is divided into two portions, that is F and D, and the value of complete is 4 MB. Means physical address space they have given is 4 MB. So I told you the formula for it. Physical address space is equal to 2 की power physical address. So how many bits will be for physical address? So it would be 2 की power 4 is basically 2, or m is equal to 20. So basically physical address, let me remove my image. Physical address would be 22. So the complete physical address we got it as 22, and because they have given frame size is 512 KB, so it is same as 19, and this will be 3 only. So frame number के लिए how many? 3. Frame offset will be same. LAS, logical address space, you know LAS is equal to 2 की power LA. That means 2 की power the number of bits in logical address, that is 32. So it will be 2 raised to power 2 into 2 की power 34 G. Right. So it will be 4 GB. And what is the page table size? So you should remember the formula for page table size. Page table size is equal to n into E, where S is the number of pages and E is the entry size. So I told you, suppose this is your page table and these are the entries. Okay, so here this is one entry and this is one more entry. So these are known as entries E. And normally in the page table what we store? We store frame number. So how many bits are used for frame number? 3 bit. So we need 3 bit, but we cannot take 3 bit. So E is equal to approximately 1 byte. Complete byte we will take for storing the frame number. So the page table size will be n, that is number of pages. 2 की power 13. You know 2 की power p is equal to, I told you the formula, 2 की power p is equal to number of pages. So here 2 की power 13 into 1 byte E. So it will be 2 2 ja 4 2 ja 8 KB. So the size of page table will be 8 KB. So the answer of this will be 8 KB. Correct? Everybody, now you have understood, I think. Is it clear? So please like the session and subscribe, share, everybody. Now we see the issues of paging. So we have two types of issue, temporal issue and special issue. You can say performance of paging. Performance of paging, we will see the two issue. One is related to time, that is temporal issue, and the second will be spatial issue. So this is related to time and this is related to space. So the first one is temporal issue, that is related to time. Temporal issue means related to time. Now here we have page table, and generally page table is stored, page table is stored in the main memory. Page table is stored in the main memory, and here you have CPU, and CPU will generate the logical address, which is divided into P and D, correct? And here this is your RAM, and now page table is stored in the, I told you page table is stored in the main memory. So you will access actually RAM two time. Okay, two time you have to access RAM, because first is for page table and the second to access for the actual page. So for first page table you have to access, and then second for page you have to access, right? So you have to use two time the RAM access. Now if you take care, suppose main memory access time is equal to M. So to access the, so effective address, you can say to access the page is equal to 2M. Why 2M? One M will be for page table and the another M is for this, to access the actual page, right? So 2M will be required. So now my aim is to reduce 2M, means I want to reduce this 2M, to reduce 2M. This is my aim. So to reduce the 2M memory access type, I will use the TLB, that is translation look aside buffer. So what will happen in TLB actually? I have CPU, CPU, and CPU will generate one address that we call is as logical address, and logical address is divided into P and D. So now here I will use one TLB cache memory, and in TLB cache memory I will keep the page number and corresponding frame number, and now this P will be searched in TLB. So this is what we call TLB. Now suppose I'm searching into this TLB, my page, but I have not found the page in TLB. So what will happen now? I will have to search my page table then. Then we have to access the page table, and 100% in the page table I will find the page number. So if I find here, so I call it TLB hit, and if I don't find the page in TLB, then I call it as TLB miss. Right, and here this is my main memory, and in the main memory I have frames. Now if I find it, then I will take the frame number from here, and the same offset I will map to here, D, and this will become my complete physical address. Also, if I find here F, then I will take it out from here also. Then the complete will become your physical address. So this is the TLB. Okay. So any doubt if you have, so please let me know. Then example, if we say, suppose main memory access time is M and TLB hit ratio is X and TLB miss ratio will be 1 minus X. Okay, and now let's say I just take the TLB access time, I call it as C. Okay, TLB access time is C unit, so it is M unit, C unit. So now, as you know, I want to find effective memory access time. In short, effective memory access time I want to find with page table or simple paging plus TLB. So the formula will look like, if I find the page in the TLB, then the probability is X, then I have to access TLB, that is C, plus I have to access main memory only one time for paging, for page. But if I don't get, then I have to spend the C unit to search the page number, but I didn't find. Then I have to check for page table, and which is stored in the main memory. And if I find it, then I have to get the physical address or data of the physical address, which is also in main memory. So the formula will be X C plus M plus 1 minus X C plus 2M. Right? So this will become our formula. And now if I take the value, suppose M value is given as 20 millisecond and TLB access time is given as 5 millisecond and TLB hit ratio, that is X, is given as 95%. Then what is the effective memory access time with simple paging plus TLB? Can you solve this example? So mean memory access time, TLB access time, and hit ratio, these things are given to us, and then try to tell me the answer. So the formula would be x c plus m plus 1 minus x c plus 2m, and here x is hit ratio, that is 0.95 c plus m, 5 plus m is given as 20 plus 1 minus x, यानी कि 1 minus 0.95, and what is c, 5 plus 2m, 20 into 2, 40. So it will be 25 into 0.95 plus 45 into 0.05. Now if you solve it, what you will get is that you have to calculate. Yes, who will tell me? 25 into 0.95 is 23.75 plus 45 into 0.05, then you will get 2.25. And now you have to add them, that is plus 26. Okay, so the answer would be this one. So now the next we'll go ahead, and before going ahead, I would like to tell you Vision 2022. So this is a batch, third batch. In this we will provide you more than 550 hours of live classes, 5000 plus practice questions, 100 plus mock test, 100 plus chapter wise study notes, and this is ideal for second year and third year engineering student. For more information you can contact on this number. And in all the batches, here is the faculty list like Murli sir, Satya sir, myself, and Ankit sir. Okay, so now we will go ahead with the special issue. Means it is related to space. Correct? For example, why we are concerned with this? So definitely 2m. I told you before this, if I take only 2m, so it would be 40 millisecond, but with the help of TLB, what we are getting, 26 ms. Definitely it is very less than 40 ms, so we have reduced the time. Now if we consider, suppose logical address is 32-bit and page table entry size is equal to 8 byte and page size is equal to 16 KB, then what will be the page table size? This is the example for understanding the special issue. What is the page table size? So definitely you can think about it. Logical address is divided into P and D, and the total is 32 bit, and page table size formula is n into e. So page size is 16 KB, 16 is 4 and k is 10. So it will be 14, and 32 minus 14 will be 32. You have to subtract it so that you will get the P. 18. Now here, so the formula is 2 की power 18 into E. E is 8 byte. 8 byte. So you can say 2 की power 18 into 2 की power 3 bytes. So finally we got the 2 की power 21 bytes. This will be the page table size, that is 2 MB. So 2 MB your page table size, right? Page table size will be 2 MB. And 2 MB is so huge, we want to reduce it. So what is the aim? To reduce the page table size, because in RAM if we load 2 MB, so 2 MB is just एक तरह से देखा जाए wastage of the main memory. So we want to reduce this 2 MB, right? So this is my aim for reducing the 2 MB, that is page table size. We can have many more things, like we can have what I can do is solution. If we see, I can increment the page size. One solution may be this, and second, I can use the hash page table, and I can use the inverted page table, right? So if I page table, page size increase. So now we will see one by one. So if I increase the page size, so again I take the example. Suppose page size for the I'm taking two cases, right? And in case number one, here I am writing case number one. I'm assuming the page size is just only 8 KB, and process is of page size is 8 KB, and process I assume 20 KB. Now total pages, how many will be there? Total pages will be 3. Okay, so one page I have, 2 page I will have, and 3 page. So one page is totally full, because 8 KB I can save in page number 1, page number 0, page number 1, and page number 2. And also page number 1 is full of 8 KB. So 8 KB, 8 KB, and remaining is 4 KB. So I will use only half, that is 4 KB I will use, and this 4 KB is just wastage. Okay, only then 20 KB I'll get now. So here the internal fragmentation will be of 4 KB only, right? Now if I assume the case number 2, then let's say page size, because what I'm saying is page size increment I want to do. I want to increment the page size. So suppose page size is 16 KB, and the process is again 20 KB. Now here how many pages will be made? 2 pages, and one page, that is page number 0, is totally full, completely 16 KB का. Now again 4 KB will be used in another page. Page number 1 में only 4 KB I am using, and the remaining, that is 12 KB. 12 KB I cannot use. Okay, so here the internal fragmentation will be 12 KB. So if I increase, what is the conclusion? If I increase the page size, then internal fragmentation may also increase. So this is not optimal solution, right? Clear? Is it clear? I hope now you understood. So if you have any doubt till here, please let me know. So this is not optimal because if I increase the page size, then the internal fragmentation may also increase. That is the reason I will take the hash page table and inverted page table. So now, before going to hash page table, I will tell you about 2020 Gradeup achievement. So we got fourth ranker, we got 39 ranker, 20 rankers, and 47 ranker. You can say 60 plus students are from Gradeup. Okay, so if you purchase any course in the Gradeup, 100% you will get a good rank. Only the thing is you need to work hard. Now hashed page table. So we have to see the hash page table. Suppose we have CPU, and definitely CPU will generate one logical address, and this is divided into P and D as usual. And now on this page number we will use hash function actually. And with the help of hash function we will get the one value, and then we have to search this value into my page table. And please remember, this is my hash page table, hashed page table. Okay, and now I will take one value from here, and what I'll do is I will map it with, suppose I got some value, maybe possible I may use the chaining. So if I'm using the chaining, then this will be a different one. Okay, for example, if I get something here not matching, so I will go with the next node, not matching, then I will go to the next node, and so on. Okay, this may be the reason that for hashing I am using the chaining. So here this will be divided into two portion, like this is the P page number and this is R. So now I will take this R value actually. Okay, and I will map R with D, and this D is the offset value. And now finally I will search it into the main memory. This is my RAM. So this will become your physical address, right? Yes, I remember. Devi, I think the name is Satyana. Nahi. You are from South, I remember, but I'm not able to remember the name. What was the name of this? What is your name, Devi? I am not recalling. I remember you. I think you were in the Nilit batch. Okay. So this is the hashed page table. Now if we see the inverted page table, so please remember one point in inverted page table, only one page table exists. Only one page table exists for complete system. That is for all process we have only one page table. Okay, so please remember, see, normally in the page table we have one page table for each process, but in inverted we have only one page table for the entire system, for the entire main memory. Srinivas, yes, I remember you. Srinivas, yes, I remember. So how are you? Vision batch में थे, right, correct. So inverted page table, what we'll do in inverted, as you know, we have CPU, and CPU will generate the address, logical address, and we have a inverted page table, and in the inverted page table, actually we have total number of frames as much, total number of pages as many as total number of frames we have. So here we have actually process ID and corresponding to page number, and we will take the values. For example, this is I, so it will be I minus 1. So I will take this I. First of all, I will this logical address is divided into process ID and page number and one more D value. So process ID and page number, I will search it in the inverted page table from here to here. Means I have to check this one and this one both, and then only I will take out the I value, index value, and this D value will be mapped same. Then only I will get the physical address, and this is my RAM. So now I will map it, and this is known as physical address. So this is the inverted page table, right? And if we take the example, then it would be clear. Please remember the number, one more point is number of pages in inverted page table is equal to number of frames. तो जितने फ्रेम्स होते हैं उतने ही हमारे नॉर्मली पेजेस होते हैं इन्वर्टेड पेज टेबल में, राइट? सो हियर आई एम टेकिंग वन क्वेश्चन. Logical address is given as 33 bits. Page size is given as 4 KB. And M is equal to 2K. You know what is M? That is number of frames. Now, conventional page table entry size is equal to 4 byte and inverted page table entry size is equal to 8 byte. Now what is the conventional page table size? You can say find the conventional page table size and inverted page table size. Okay, can you calculate this? I will give you only 1 minute.